How about this first one about crystalline and amorphous? Can you give me an analogy for the orderly one? Like a big object. Legos? Anything else?
Balls that you expand out.
I don't know what those are called either. Yeah. What was that one that had the wooden wheels that had wood dowels that you would? Those are Tinker Toys, not a Rector set. Yeah. Disorganized. What do you want to say as an analogy for that? Jess's kids toys. Something else? Pile of sticks. I don't know about that. How about several extension cords in a box? Like, you didn't throw them in there and like mix them up and jumble them around, but when you go to pull one out, they all come out, right? All of them. Why is impurity not necessarily a bad thing? Can make it stronger. What else can it do?
No, more brittle, but
It could make it.
it's splitting the same way it knots.
It could make it less brittle. If I'm talking about zinc as a metal and I mix copper in with it, then the zinc definitely became less brittle. The copper became more brittle, but the zinc definitely became less brittle. I could. So going along with that same thing, increasing flexibility. Anything else super important? So you can have the thing become less corrosive or more corrosive depending on what the situation is. What do we mean by folding a sword? It could add impurities to it, but what's the process of it? What do we mean by folding it? Melting it, heating it and beating the hell out of it. And then once it becomes flat enough, this is obviously not like a sword, it's super wide, then you can bend it in half and fold it over on itself. So it's a flattening. If you flatten and refold, or flatten it and fold it over and then do that maybe a dozen times, that would be a very, very expensive piece of weaponry. That process itself is very, very time consuming and labor intensive. I'm guessing that we would make things a lot different than we were today, and it would be a hell of a lot easier for us because instead of having some dude with giant forearms, we'd just have like a hydraulic hammer beat on it. Every once in a while, I'll be watching a movie or something, and I'll be like, the sword was folded 200 times, and it's the strongest of like 200 times would make that thing as brittle as like a pencil. Too many impurities would pound it into it, so sometimes I get a little overboard with science in movies, but I think we all know that. Okay, so what we need to, I should have wrote this word corner in here. So this distance here to this distance here is that distance. So from here, because that's the diagonal through the, so I can't use, when we did the simple cubic, it was really easy because if I measured the distance between the lattice points, I just took that number times it by 2 and now I know the radius. But I can't do it with this body-centered. How come? Well, there's a gap right there, right? So if I just took I can't just take that distance and multiply 2 because I don't know how big that gap is. But so what I need is a distance where all of the points are touching each other, and that happens here. So what I end with here is I have this right here, bless you, is a radius. From there to there is another radius. From there to there is another radius. And so from there to there is a final radius. So this distance here is 4 times the radius. So if I know what that distance is, then I can figure out what the distance of the individual r's are. And so I'm going to use a squared, b squared, c squared. And I know that a and b are going to be equal to each other. So if I throw in, like, there's an a distance, there's my b distance, and there's my hypotenuse, my c distance. Are we okay with that? So what I can do is just call this x squared plus x squared is equal to c squared, since those two things are the same thing. So then I can punch in 4.073 times 10 to the negative 10th. And I'm going to square that and add to it the same thing. Square that, and that equals c. And if I square root the c squared and I square root this side, I'm going to get c, which is equal to r. And what do I get here? This really is just how good are you at punching this into your calculator, this last part. So it's sort of a parentheses, I want to say nightmare, but it certainly isn't. Easy as 0, 4, 3. E, negative 10. And if you're not using the E key on your calculator, you're really putting yourself at a disadvantage, because order of operations is going to force you to put in more parentheses.
What is it?
It is the E key on your calculator, and the E stands for, is that right? I forgot something. 1 second. Just a second. All right. Okay, I got 5.76 times 10 to the negative 10th. Do you remember what pico stood for? Talked about it very briefly. So milli is 1,000th, and micro is a millionth, nano is a billionth, and pico is a trillionth. So it's 10 to the negative 12th. So if I make this 10 to the negative 12th, what would this number become here, this 5.76? Other direction. Does that make sense? Because I made this 5.76 number bigger by 100-fold. And so that means I got to make the 10 to the negative number smaller by 100-fold. So then I can change this to just be a picometer. So 576 picometers, which is the number that people use, or the unit that people use to talk about atomic radii. The E key. Let me just pause this room. Okay, how about this last one? What's the reasoning behind the X-ray crystallography instead of gamma or UV? X-rays wavelength when I look at the size of an X-ray, the length of that wave from crest to crest, that range that constitutes X-rays, is equal to the actual size of atoms.